There's the button. All right, so good morning, guys. This is going to be uploaded here in a minute, but I want to talk to you about one of the things that happened in the prime factorization workspace. It's workspace number 2 out of this trimester's math. And in that prime factorization workspace, they talk about a prime factor tree. And so that's what I want to do here. I want to take the 32, do some work on the side, and I want to talk about the prime factor tree for 32. Some of you might have seen this already as you're working through that workspace, but the goal of this question is to actually try to connect what happened in the prime factor tree to the rules of exponents so that will help us simplify these types of expressions. 32, I'm going to, first of all, think about the ways that I can factor a number out from it. 32 is even, it ends in a 2. So I'm going to divide both sides by 2. That gives us 16. Okay, keep going, right? In a prime factor tree, these are the branches of the tree. In a prime factor tree, the ends or the leaves of the tree should all be prime numbers. So if this is a prime number, can't divide it by anything, stop and go to the other number. Take the 16, for example. 16 is even. It ends in 6. 2, 4, 6, 8, those are all even. So therefore, I can further divide 16 by 2, leaving me with 8, right? So 16 is 2 times 8, and on this branch, we have a prime number, so we stop. But on this branch, we have a number that's not prime, because I know 8 can be divided by 2. And we continue, kind of a lopsided tree, if you think about it. It's all aiming that way. So we continue going down the branches. This branch stopped, this branch we stop, this branch we stop, because those are all ending in a prime number. 4 is not prime, 4 is even. 4 can be divided by 2, leaving us with 2 times 2. In fact, fact of mathematics, 2 times 2 times 2 times 2 times 2, all of them multiply up to 32. So I'm going to take the 32 that's here, and I'm going to break it apart into all of these prime factors, which is 2 times 2 times 2 times 2 times 2. Now, there's another way to write that, right? 2 times 2, that many of them, there is 2 to the 5th. So just to be aware, there might be a reason for us to want to compare that many 2's to the fact that there's a 5 exponent. I'm not going to do that right now, though. I'm thinking about breaking the thing all the way down. Now, I wanted to include this one. If you watched the other video difference in the earlier class period, I didn't have this scenario. I didn't have a power to a power. And so I want to make sure I comment on that right now. A squared is an expression inside the parentheses. And the 2 that's on the outside, it tells us how many of these a squareds there are. But then the fact that it's a squared means that it's a times a, written twice. So we have times a times a times a times a. There are 4 a's, in fact, because we can shortcut with the power rule, multiplying those 2's together. And then this is a b. I know it looks like my b letters don't look quite like b letters, look like 6's. It is a b, and therefore there is a single 1b exponent, 1 at the end. And so I'm just going to put that right there. This is all over the fraction bar. And on the bottom, I want to do the same thing. I want to prime factor 48. I mean, maybe you know that 16 is the greatest common factor of both 32 and 48. Maybe you didn't know that. So how can we shortcut the process? Actually, the shortcut is to expand, and you'll see how I cancel things out. Let's do the prime factor tree for 48. So 48 prime factor tree splits. Well, let's see, it ends in an 8. Because it ends in an 8, it can be divided by 2. So 48 goes into 2. If you cut 48 in half, 24. That's the way to think about like why dividing out by 2, factoring by 2 is easy. You're just cutting it in half. So 2 times 24 together make 48. Those are 2 factors of the 48 thing. 24 is not a prime number. 24 has a digit at the end. It's a 4. 4 can be divided by 2. Okay, cut 24 in half. That's what we mean by factor out the 2. 12. 12 is another one. So we just keep going down the line. 12 prime factors. Go down the branches of the prime factor tree. 2 times 6. 6 can be divided by 2. So if we have a 6 and we divide it by 2, we are left with 2 times 3. So actually, 48 would be 2 times 2 times 2 times 2 times 3. All of those 2's are multiplied together and the 3 at the end. So we're going to take that 48 and we're going to prime, expand, factor it all the way out. 2 times 2 times 2 times 2 times 3. That makes 48. Now, there's a single a in the bottom of the fraction. Technically, that means there's a 1 exponent. Maybe that matters, maybe it doesn't, but just as I'm saying consistently, 1 single a on the bottom of the fraction. And then last of all, b to the 3rd power. How did I write that b so fancy? I went like this. Ooh, I like that, a little cursive. Okay, don't tell me that's a 6, it's a b. Now, if there's something that's consistent on the top and bottom of the fraction, we can cancel it out. Because for example, 2 divided by 2 is 1. So if you have the same thing on the top and bottom of your fraction, because of the process of division, equal things being divided, 2 divided by 2. 2 divided by 2. 2 divided by 2. Now, 2 divided by 3, those are not equal, so we're not gonna mess with them. Don't you dare touch them. Part of our answer. We look at the next thing after that, which is the letters. So here we have A. I know it's grown-up math time, right? It's algebra. So grown-up math time says if we have letters involved, that A and the A on the bottom, they work together, they cancel each other out, just like 2 over 2 does. A divided by A is 1. But all of these A's, they don't have anything on the bottom of the fraction. So they're gonna stay consistently on the top, as in A times A times A, or A to the 3rd. So we'll put A to the 3rd on the top of the fraction. Almost done, stick with me. The B that's on the top of the fraction, and one of these 3, just pick one. This B can be canceled with U. B divided by B is 1. You're still left with 2 B's on the bottom. So B squared, answer. That is how we use prime factorization, the prime factor tree for a number, the prime factors of exponents and exponents to simplify an exponential rational expression.